In this video we present an example for spin-spin coupling for a molecule that looks like this. Okay, this molecule has two groups of protons. One is HA and the other one is going to be HB, so you will get two signals in the proton NMR. The goal of this video is to try to discuss how the splitting patterns of those two signals will be. Okay, so first the signal of HB is going to be straightforward if you have seen the prior videos, okay, because it turns out that the signal of HB is going to be split by this H sub A. Okay, and we know that the H sub A nuclei can be spinning all in two directions towards the field or against the field, and each one of them happens approximately 50% of the time. What that means is that the nuclei in H sub B see an overall field that is 50% of the time the contribution of the external magnetic field modulated by the electronic environment and spin up of this H sub A, and 50% of the time the overall magnetic field seen by this H sub B is going to be this external magnetic field plus a contribution that is negative from the 50% of the protons that are spinning such that the induced magnetic field is pointing down. Okay, so what that means is that you see two different types of fields, okay, and that is going to be a doublet. Okay, so A to B is going to be split into a doublet by the action of one NMR-active nucleus, H sub A, which is within 3 bonds of those protons. Now, the interesting aspect of this video is to try to examine how the splitting pattern of HA is under the action of these H sub B's. Alright, so again, each one of these H sub B's can be 50% of the time pointing up or 50% of the time pointing down. When I say pointing up or down, what I mean is that, well, those spins, those H sub B spins, are going to be precessing around the external magnetic field, and the induced magnetic field is either pointing towards the field or against the field. Okay, that's what I'm trying to say here. Again, this H sub B will be 50% of the time pointing up, 50% of the time pointing down, and then 50% of the time pointing up, 50% of the time pointing down. Right, so when we analyze all of the contributions, not the contributions, but the combinations of all of these spins, we see that one of the possible combinations is that the 3 spins of H sub B are pointing up. Okay, that is one possibility. Another possibility is that, well, 2 of them are pointing up and 1 of them is pointing down. Okay, and these situations are all the same. The overall magnetic field is exactly the same in all of them. Okay, so 2 pointing up and 1 pointing down. Then you also have that the possibility exists that 2 are pointing down and then 1 is pointing up. Okay, and finally, the only other combination is that the 3 of them are pointing down. Okay, so notice that when you actually see all of the combinations, there's 8 possible combinations, and that means that this is going to happen 12.5% of the time, this is going to happen 12.5% of the time, and the rest, the remainder, okay, that rest of 75% of the time, you're going to be split into these 2. Okay, so that is going to give you 12.5% times 3, so 37.5%, 37.5%. Okay, you have those 2. Right, so then the splitter is going to be as follows. Okay, you have the signal of HB, of HA, sorry. And again, what you're going to see is that 12.5% of the time, you're going to see an external magnetic field, okay, this V sub naught, corrected by the electromodulation, and then up, up, and up. You will get that signal right here. Okay, it will happen that 37% of the time, you're going to get this V naught, 1 minus sigma, okay, and then 2 up and 1 down, okay, and then 37.5% of the time, you're going to get the external magnetic field modulated by the electrons, and then 2 down and 1 up, and then 12.5% of the time, you're going to get the external magnetic field V naught modulated by the electrons, 1 minus sigma, and then the 3 spins pointing down. Alright, so again, this happens 12.5% of the time, 37.5% of the time, 37.5% of the time, and then 12.5% of the time. What that means is that the intensity of the signals is going to be 1 to 3 to 3 to 1. And again, that is the ratio of 12.5 to 37.5%, 37.5, 12.5. Okay, so when we look at the NMR spectrum of this molecule overall, it's going to have this signal, this type of splittings. Okay, we get that. The NMR spectrum is going to look like this. The signal of HV is going to be a doublet, okay, where the relative intensities are going to be 1 to 1. Okay, that is the signal due to H to B. And the signal of A to A is going to be a quartet, where the relative intensities are going to be 1 to 3 to 3 to 1. Okay, that will be your H to A. What is more, if we integrate the area under these peaks, okay, the overall area is going to be 1, and when we integrate the area under these peaks, the overall area is going to be 3, because this is related to how many protons you have contributed to the signal and how many protons you have contributed to the signal. Okay, to summarize this spin-spin coupling modeling here, what we actually have to conclude here is that, again, the splitting has to do with NMR-active nuclei that are within 3 bonds of U, okay, but are a different signal. Okay, that's what what causes the splitting. But the intensity, okay, the orbital intensity is caused by how many NMR-active nuclei you have contributing to that signal. Okay, so in the next video we're actually going to generalize all the findings that we have for spin-spin coupling, and then come with very useful universal rules to predict how the splitting pattern would be for any molecule that we wish.